Let's go to a first case study where we did virtual piloting in the technology selection phase. So our customer Waterboard De Dommel in the Netherlands, some of the people are also joining this webinar right now. They had the question, well, if we go for ozone, what would be the dose we need? How much bromate would be formed? What would be the cost implications for us at this specific plant? In the Netherlands, there is a lot going on right now, also in terms of regulatory developments. For example, they already have a list of 11 indicator components from which you have to remove 7. And but also, yeah, there are other questions. For example, what if the regulation would change in the future? What if it would become 18 indicator components and we have to, for example, remove 11? Can we do some additional testing? Waterboard De Dommel didn't really feel like building quite an advanced pilot on site, so we went for the simulation route. How did it work? Well, we started collecting some on-site data offline and online. Online means pH, ammonia, which is already there, and also UV254, for example. Offline means DOC, nitrites, carbonates. That's step number 1. And step number 2 was taking a couple of samples on site, and you can see it on the picture, where 3 of us have been on site, and we had collected a sample, which is in this box, sent to a lab for some basic ozonation tests on which we calibrate our model. So if we then feed the calibrated model with the real-time sensor data, we can start the virtual piloting. And in fact, it's not really a pilot. You can build several full-scale plants. So we have built several virtual full-scale plants that were then fed with the real online sensors at the plant. There's one big difference, of course. No plant has been done here. And also, there was not a single micropollutant analysis needed. So that's really key here. Some inputs we got, flow rates, ammonia, DOC profiles. This is a typical day profile. Of course, we did some longer data collection, but this is just one day, 3 a.m. to 3 p.m. You see the flow increasing in the morning. These are the typical patterns observed in wastewater treatment plants. On the other hand, if we look at the lab calibration, this is some of the data. You can see the ozone decay very fast, and then it goes down, and at a lower dose, which is still high in this case, by the way. But it's just to illustrate that we have done some calibration. And again, we come to the matrix here, very matrix dependent. And then we did some validation, not really calibration, because our model didn't need any calibration for bromate. So here you see the bromate being formed as function of time in a batch experiment in the lab, and the model is quite nicely predicting the levels. So at very, very high doses, we are talking about even 20 in this case. There are different runs were done, but with a dose of 20 of ozone, you have around, in this plant, around 15 micrograms bromate, which is still low if you look at the ozone dose.
Let's go to the virtual full-scale installation of Waterboard De Dommel. So the model as you see here running is running on an influence of flow rate, UVA, DOC, lots of, it's a nice set of 1 month long data, actually even more, which is has been measured at the outlet of a wastewater treatment plant. So here you see the influence of our ozonation plant, which is the effluent of the upstream wastewater treatment plant. What you see here, the effluent wastewater from the treatment plant is arriving to a split, which is a bypass where the high peaks in outflow are bypassed into the overall, plant effluent. But most of the flow is directed to our ozone installation. That's sized, which is sized to treat most of the water flow coming from exiting the wastewater treatment plant. Now, the first thing that we encounter here, it's another split, which is directing 20% of the flow to our side stream injection device. So in here, you have the gas transfer of the side stream injection, which very efficiently injects ozonated gas at a certain concentration, depending on the generator in use, and is controlled, can be controlled with different control strategies. Here you see different examples of controllers, like a flow proportional controller, DOC proportional control, even micropollutant-based controller, because that's the next step. We can look at it later, basing your actual dose on a specific micropollutant to be sure to be in the legislation boundaries. And also another one, the UVA proportional controller, so ensuring that parts of the UVA fraction is knocked down, and basing on that your ozone injection. So after the side stream injection, after injecting your needed ozone, then you re-enter the mainstream and you let react in your volumes in the rest of your installation. Let the reactions happen of ozone, radicals, micropollutants reaction, bromate, and so on, until you discharge. And with this model, you can go and look at the what is happening inside your installation. Actually, what is the effluent, bromate, for instance, at different points. And what is interesting here to see, it's also what Wim will talk about later, will mention again, is the ammonia relation, the ammonia influence on bromate, because of the formation of monobromamine and dibromamine, which is sequestering bromide ions. And this is an interesting detail because it really influences the bromate formation, and meaning that the control of your upstream installation, the wastewater treatment plant, has an impact on your bromate formation possibilities then. But also you can check the UVA fraction that is exiting the plant and the overall effluent at the outlet of the whole plant site. So what I was talking about, you see this red line here is where the bypass kicks in. So this is well, a reasonably small rain event, but which caused a sufficiently high flow to get bypassed here. And here is the capacity of the ozone installation treating all the rest of the days of the flow during the rest of the days. So what is interesting to look at is the amount of the micropollutants. Here are listed the interesting ones for Waterboard De Dommel, and you can look at how they are removed in time in the different days of simulation, depending on as a result of a whole complex net of reactions generating and balancing ozone and radicals concentrations. What you see here is the relative removal of the compounds. It's mostly what regulations look at, and the ones that you see at the top here are the ones that are removed, let's say, better or to a larger extent. You see mostly the ones that like diclofenac and carbamazepine that we have seen earlier, sensitive to both ozone and radicals. You will find it easily here. Whereas the more you go down, and the more you find like recalcitrant, more resistant and die-hard compounds, like ibertazan. Nonetheless, you can monitor crucial variables that will be useful and very important to size your real installation. And based on this prediction, you can actually think of really know which one is the generator that you will need the size of your installation to make sure you won't have residual ozone in the effluent, but also you won't have oversized your installation and your capex as well. So you can look at the ozone dose, the ratio ozone DOC, the average micropollutants removal, and so on and so on.
But this is the most interesting part, of course. If you have this virtual full-scale installation, you can just release the model, and in a matter of a couple of weeks, we have tested all kinds of scenarios, different dosages, different dosing strategies, and then for each of the scenarios, you can make, for these 11 Dutch indicator components, the analysis of how much are above the 70% threshold. 8 to 7 to 10, it depends on the dose, of course, but you can easily visualize this and then, of course, make an analysis of this. Again, what if the future regulation would change? We have 19 instead of 11 components. We just add the components, and then you see the extended set with the same scenarios here. And then you can look at 70% or maybe future 80% target removal percentages. So this is the combined flow of both the bypass and the ozone plant. Of course, you can visualize both. And in some of the scenarios, we assumed 10% removal at the biological site. And in another scenario, more, let's say, best case, we assumed a 30% removal. In reality, it's somewhere in between. Of course, interesting output of such an exercise, including flow rate changes, is what is the kilograms per day of ozone you need in all of these runs? And also, what is the OPEX? What is this OPEX plus investments you have? And also, yeah, for example, in cents, euro cents per cubic meters. Quite high at this plant because it's a very small plant. But you can visualize all of these things and also then start playing with your dosages. Conclusions of this study were, well, the cost and time for real-life piloting would have been orders of magnitude higher. We are now talking about 6 weeks. If you would have put a pilot on site, we would have easily talked about 1 year or more. We are not saying that on-site piloting is not valuable or cannot be valuable, but we have observed that in many cases, the value can be better or the process can be much more efficient. So yeah, also ballpark costs wise, it's very different. Huh? You are talking about like 10,000 or a couple of tens of thousands of euros instead of hundreds of thousands of euros, including man hours and analysis of micropollutants and things like that. So there's much more knowledge gained and yeah, insights.